Morning, yo.
Morning. Oh, it's 8 o'clock. Okay. Okay. So let's see. I finished my Calculus 2 exams. I will start yours today, and it'll probably take me a couple of days, but I will definitely get them back to you by Friday. Um, okay. And you also have homework due this Friday. Okay. So you have to do your homework, and I have to grade your exams. Let's see. Oh yeah, I did. I called Spectrum. I hate calling Spectrum. It's always torture. But and I increased my internet speed by 5 times yesterday. So I hope that
Gee, you
my
think Spectrum's bad? Try Verizon right now. Now, we got they sent us a freaking booster to help our thing, and it was meant for a landline. And when Dad called the tech guy, he said he had no idea why they did that.
I can't help with your problems. I can only do what I can about my problems. But yeah,
I know, I'm just saying that every internet company is just as bad as the other.
Yeah. Well, yeah. Since my entire life is now lived via Zoom, I figure I better do what I can. Um, okay, so let's see. We were talking about logs. We're going to keep talking about logs. So I'm going to share my screen. Okay, that's my other class. And this is your class. Okay, so we have defined this new function, ln of x, which is natural logarithm. We're going to prove today that it really is a logarithm function. Why it's natural as opposed to some other logarithm functions, I probably won't get to until tomorrow. But okay, so we started looking at this function. Ln of x is defined to be the definite integral from 1 to x of 1 over t dt for x greater than 0. So the domain of this function is the positive numbers. Yeah, and we also showed yesterday that the natural log function is increasing. Okay, it's a natural log, but people usually say ln of x, okay? Ln of x is positive if x is greater than 1. Ln of 1 is 0. And if x is between 0 and 1, ln of x is negative. We know from the fundamental theorem that the derivative of ln of x is 1 over x. And then we can compute the second derivative, which would be minus 1 over x squared. And since minus 1 over x squared is always less than 0, that means that ln of x is concave down. And yesterday we got as far as showing that the graph must look something like this. Okay. And, well, we still have much to determine. For one thing, it's concave down, but what's to say that maybe it doesn't just kind of level off like that? Have a horizontal asymptote, or does it just increase forever? Kind of looks from what I've drawn that maybe it levels off. Well, how do you tell? So we want to know is ln of x bounded above? That is there some line that I can draw below which the whole graph is, okay? Well, it's not. And I can prove it to you. Yesterday, we saw that ln of 2 was between 1/2 and 3/4. In particular, it's greater than 1/2. Okay. So suppose I pick any positive number, and I'm thinking big positive number. So it's a positive number. Well, then ln of 2 times m, so I may as well assume m is greater than 2. Okay. ln of 2 times, oh dear, I need to show you. Okay, before I can do this, before I can answer this, I need to show you that the log, that ln of x really is a logarithm function. Yeah, because I want to use one of the rules of logarithms here. Well, let me just go ahead and do it, and I'm going to prove this rule works in a minute. Okay, didn't think ahead enough. Okay. Let me answer this later because I need to use. All right, let's prove that ln of x is a logarithm function. I know you've seen logarithm functions before, but what makes a function f of x is a logarithm function if, okay, the domain of f is the positive numbers, and that's true about our function. We do have that the domain is a positive, is a set of all positive numbers, and some algebraic properties hold. ln of x times y is ln of x plus ln of y. ln of x over y is ln of x minus ln of y, and ln of x to the r is r ln of x. These algebraic properties must hold. And let's see, I should put some conditions on x, y, and r. X is greater than 0, y is greater than 0. R can be any real number. Three properties must be satisfied if this function, ln, that we have defined really is a logarithm function. And I'm going to show you that these three properties hold. Okay, so first, for x and y positive, ln of x times y is ln of x plus ln of y. So proof. Okay. Well, by definition, that is this definition, okay, ln of x times y is the integral from 1 to xy of 1 over t dt. ln of x is the integral from 1 to x of 1 over t dt. And ln of y is the integral from 1 to y of 1 over t dt. Okay, so I want to show that ln of xy is the sum of these two numbers. So let's look at ln of xy. Okay, that is the integral from 1 to x to xy of 1 over t dt. And I'm going to use a property of integrals, the one that says if f is continuous on an interval containing a, b, and c, three numbers, then the integral from a to c of f is equal to the integral from a to b of f plus the integral from b to c of f. That I can break that one interval, which would be one to a to c, and I don't really care whether the a is less than c or the c is less than a. This statement's true. This is one of the properties of integrals. Okay. Well, definite integrals, I should say. It's not definite. There is no interval to break up. Okay. Now, our function ln of x definitely is continuous. Its domain is all the positive numbers. It's continuous over the positive numbers because it's got a derivative. The derivative of ln of x is 1 over x. Any function, so it's differentiable, any differentiable function is automatically continuous. Okay, so continuity, not a problem. But this property says that I can break this integral up into the integral from 1 to x of 1 over t dt plus the integral from x to xy of 1 over t dt. This property. All right, so we have, and note that this thing right here, that's ln of x. So I'm hoping that this is ln of y. And it is. And let me show you. And I kind of planned ahead, so I can remember how this works. I'm going to look at the integral from x to xy of 1 over t dt. All right, and I'm going to do a u substitution on this. I'm going to let u equal to t over x. Okay, now let's think about some things. This is a definite integral. What does t represent? T represents any number between x and xy And maybe x is less than xy, or maybe xy is less than x. So one of these at least is true. T represents any number between x and xy. Somebody entered the waiting room. Okay, here I am. Yeah, T represents any number between x and xy. X is an endpoint, okay? Relative to this integral, T is the variable. X is fixed. X is a constant right now. So is Y. All right. So if I let u is equal dt, okay? Because the derivative of t over x, remember x is a constant, x is positive. So t over x is defined. But this is really 1 over x constant, 1 over x times t. So the derivative just is 1 over x. Okay, so that means that x du is equal to dt, and also that, okay, I know that okay, I don't know which way this inequality goes, whether it's this one or this one. But I'll just look at this first. All right, t over x. So if I multiply through by 1 over x, x is positive, so the inequalities stayed in the same direction. So 1 is less than or equal to t over x is less than or equal to y, and u is t over x. So u is between 1 and y. Now, if the inequality was this way, it would work out the same way. Okay. If it was the other case, so this is possibility 1 or 2, still the case, I can multiply through by 1 over x. And I've got y less than or equal to t less than or equal to 1. Okay. So either way, excuse me, which is relative to my new variable u, my endpoints are 1 and y. So this becomes, with this substitution, this becomes the integral from 1 to y of 1 over u yes, 1 over u du. Because let me come down and put in another step. Okay. Is equal to, okay, 1 to y, and then t is replaced by, let's see, t is u times x, and dt is x du. and the x's divide out. This is just the integral from 1 to y of 1 over u du. And okay, it doesn't really matter what I put in here for this letter or what I named that letter. Here, okay, u represents anything between 1 and y. And I don't know which one's the bigger one. But that means this is ln of y. Yeah, that's you. Sometimes you call this the t here, the u here. People call them dummy variables. I can name it anything I want, well, except for y or x, okay? Because in this problem, y and x have another meaning. But anyway, I can call that thing anyway, anything I want. So that shows then that this integral is ln of y, and ln of x times y, which is by definition this definite integral from 1 to xy of 1 over t dt. By property of integrals, I can break that into the integral from 1 to x of 1 over t dt plus the integral from x to xy of 1 over t dt. I don't want you. And this is ln of x, the definition. We just showed that this integral is ln of y. So we have proved that ln of xy is ln of x plus ln of y. Okay. So that's that first algebraic property, that any logarithm function must satisfy. That one's really easy after you do this one. Amazing that we have defined a function with calculus. We have defined this function ln of x in terms of definite integrals and the out of that definition. Kind of amazing. Let me prove this third one, or I'm going to be able to prove it as long as R is a rational number. Proving it for the irrational numbers is a little bit beyond us at this point. You really need to have an analysis course before you can see that. Okay, are y'all still there?
Yes, ma'am. Yes, ma'am.
Okay, good. Okay. But before I go on, are there any questions?
I mean, it all kind of happened so fast.
You think, okay, you want me to go through it again?
I mean, nah, I just, from the get-go, you gave us those three, I guess you can call them formulas or whatever. But did we use the first one simply because the original function that we were looking at was from x to xy?
Yeah. Well, okay, I want to prove this statement. Okay. And to prove this statement, well, what does this mean? A mathematician always goes back to the definitions. Okay. So how have I defined the natural log of a number? I defined it to be, okay, my definition right up here, for any part. This is my definition that I made. Yeah, and you can define anything you please. You're allowed to do that in mathematics, but it must it must be clear what satisfies the definition and what doesn't. So you can't make a definition where you can't tell whether, oh, my couch is in that, it satisfies that definition or not. I got to know. Okay. Yeah, mathematicians use words very carefully. When you make a definition, you want to say exactly what you want it to be. My definition here is as long as x is a positive number, I'm going to define this function to be the definite integral. Okay, so ln of x is by definition the definite integral from 1 to x of 1 over t dt. I made it. I got to stick with it. Okay, so now I'm going to be using this definition to really show that this new function I've defined is what you call a logarithm function. Okay, and okay, I didn't decide what a logarithm function is, but mathematicians have. A function is called a logarithm function. Well, first of all, its domain's got to be the positive numbers, and it has to satisfy these three algebra properties. Okay. So if I'm calling my function a logarithm function, I must show that my function satisfies these three properties. Okay. Daniel, does that help?
Yeah, so you're basically proving your definition by these three.
Yeah.
Gotcha.
Yeah. So I want to show that this function that I have defined does satisfy these three conditions. And really, only then am I allowed to call it a logarithm function. Okay, so to prove it, I'm going to start with part A. That's the part we've done so far. Okay, so I got to start with my hypothesis and reach my conclusion. Really, my only hypothesis is that x and y are positive. Okay, but what is my definition of ln of xy? It is the definite integral from 1 to xy of 1 over t dt. My definition of ln of x, it's the integral from 1 to x of 1 over t dt. And ln of y is the integral from 1 to y of 1 over t dt. Okay, so I have, this is how I've defined ln of xy, ln of x, ln of y. And now let's start with this. And I want to show that this is the sum of this and this, okay? But I have to go through some steps to do that. Well, ln of xy, I can break this integral up into the sum of these two integrals. And I'm allowed to do that because of one of the properties of definite integrals. And that says that if you have a function that's continuous on an interval containing a, b, and c, three numbers, then you can break up the integral from a to c of f into the sum of the integral from a to b of f plus the integral from b to c of f. And that's regardless of the order of a, b, and c. Okay, so I'm using this property to say that ln of xy is the sum of those two integrals. Well, that one right there, that is ln of x. And I'm hoping that this integral is ln of y, but I still have some work to do to show that. But here's where we did it. If I look at this integral from x to xy of 1 over t dt, and I use a u substitution, okay, so it's a strange one. And then my u substitution here, actually, the only purpose of it is to change the endpoints. change the endpoints by kind of sliding the function down in a way. But okay, this is a legal thing I have done. Okay, you must stay within the rules in mathematics. You absolutely must. A rule is a rule, and you do not break it. But that doesn't mean that you can't do all kinds of things within the rules. It's kind of like saying, okay, I'm in this building. I can go from room to room or floor to floor, but I'm not allowed to walk through the wall. Okay, that's kind of what the rules do. They give you structure, and you're not allowed to violate it. But within that structure, there's plenty of room to manipulate and make your own stuff work. So what I'm going to do is do this U substitution. T is my variable in my original integral, the dummy variable. I'm changing it to U. So there, that dummy variable. Okay, but how am I going to do that? I'm going to let U be T over X. Remember, T is a variable relative to this integral. X is a constant. It's an endpoint of an interval. Okay, so either T here in this integral represents any number between X and XY. So X is fixed. Then U is T over X, which is 1 over X times T, and that's just a constant. So dt is when, that means that X du is dt. Also, if U is T over X, then T is U times X. Okay. So, but this allows me to go from endpoints of X and XY to endpoints being 1 and Y. Okay. So that it's a change of variable there. So it got me to this integral. And okay, I put steps in down here to show that. So I started here. I want to get here. But what is T? T is U times X. Okay. What is dt? dt is X du. So this T is U times X, dt is X du. And my new endpoints relative to U are 1 and Y. So yeah, so the X, XY corresponds to a new endpoint of Y. The X corresponds to the new endpoint 1. And we kind of went through the argument to show that. Okay, but this gets me there. Okay, that is ln of y. Because yeah, the letter I put in here, as long as it's not y, doesn't matter. And yeah, so ln of y, this really is the same statement. Because here, 1 less than or equal to t less than or equal to y. And here, 1 less than or equal to u less than or equal to y. I'm just calling that dummy variable a different name. I didn't put that up here because t had already been used for something and it gets a little confusing, okay? Okay, so this is a proof. This is what you call a proof. And I hope that helped. And, well, okay. I don't know. My students usually don't like proofs. I do, because I'm a mathematician, and I do this for a living, and I think this is so beautiful. But, yeah. Okay. Well, we need to go on, I guess. But, well, would anybody else like to ask a question? Or Daniel, you too? I'm just trying to show you some things that I think are amazing. And y'all are still there, aren't you?
Yes, ma'am.
Yes, ma'am.
Okay, good.
So
Okay.
towards the end of that, where you found ln of y, there is no need to plug back in what we substituted, huh?
No. Yeah, I just wanted to show that this was the same thing as this.
Oh, okay, I see what you're talking about.
Okay, yeah, and it's like, why would you want to let u be t over x? Well, because that's what I need to make this work for me. That's why. And you're allowed to do these kinds of things. Okay. I could let u be t squared if I wanted to be. Now, whether that would help me out or not, and it wouldn't, is another matter. So a lot of this is kind of planning ahead and making, and you want to go from the start, your beginning place, your assumptions, and go step by step logically until you reach the conclusion. And then it's what you call a theorem. Okay. Well,
I hate to interrupt again.
Okay.
But going back up to the top, I'm kind of having a hard time following how like 1 over t is actually just 1x times t. 1 over x times t.
Okay. Well, okay. T over x. This is another algebra rule. Okay. Right? A over b just means the same thing as a times 1 over b.
I mean, I understand that, but our original function is 1 over t. Where does 1 over x come in?
Okay. Oh, okay. I think I see what you were asking about. Yeah. In here, it's 1 over t. Okay. I made this up. All right. That's what I said. Let this is math talk. Let u be a new function. U is the function t over x. I have defined u to be t over x. You can define things in mathematics any way you want. Whether they help you do anything is another question, okay? But this definition is going to help me show that this integral is the same as that integral.
So is u substituting t, or is it substituting 1 over t?
I'm substituting t.
Okay, that makes sense.
Okay, yeah. And in fact, that's why, let's see, down here, actually, yeah, there's kind of a step in between these two. This one, t is, from my definition that I made up. I made this definition. I got to stick with it. Okay. You don't get to change it. Not in the middle. You make a definition, you stick with it. And according to my definition, T is U times X, right? Because U is T over X. So if I multiply both sides of this by X, I get that T is U times X. And also dt, according to the definition that I made up, dt is x du. So this, I'm doing my u substitution carefully. T gets replaced by ux. dt gets replaced by x du. And my new endpoints, okay, we already showed that above. My new endpoints are 1 and y now for this new variable. U now represents any number between 1 and y. And, okay, so 1 over ux dx du is equal, that integral is equal to that integral. The x's cancel out, and that leaves me with that integral. And that's what I wanted. That is ln of y, my definition. Okay. Okay. But Daniel, I'm really glad you want to understand. Okay. This does take a little absorbing. And I've been a mathematician now for over 40 years. And I've been teaching calculus and math courses for over 40 years. A lot of this is automatic to me. It's just part of the way I think. It's not so easy when you're young and you're beginning, okay? You don't have 40 years of experience under your belt. I do. But you're young and beginning, and I'm old and ending. So I'm just trying to pass along a little knowledge. Okay. All right, let's move on to this. Oh, what time is it? Oh, we're okay. This one, I'm going to prove step by step, at least for the rational numbers. This is another theorem. Okay, and let's see. It's true for all real numbers. But right now, okay, you have not had an analysis course, so I can't show you a proof that would be above your level. But for rational numbers, I don't need to go to that level. So ln of x to the r is r ln of x. And of course, x is still positive, okay? Domain of the natural log function is positive numbers. Okay. I'm going to prove that it works. This statement works for r equal to 0. Okay. So that's one number. That. I have a lot more other numbers to consider, but okay. What would this statement be? ln of x to the 0. Well, if x is positive, x to the 0 is 1. That's a basic algebra rule. And ln of 1 is 0. And 0 times ln of x, well, ln of x is a number. 0 times any number is 0. So it is true that ln of x to the 0 is 0 times ln of x. Check. Okay. Now I'm going to prove that this works for r equal to 1. You say she's not making much progress here. But okay, but ln of x is to the first is just ln of x. X to the first power is x. And any number times 1 is that number back again. Okay. So this is true. Check. Okay. Works for r equal to 2. Let's see. ln of x squared. Well, x squared is x times x. And we just proved that if you have a product of two numbers, that you can break it into the sum of the logs of those numbers. Okay. ln of x times x is ln of x plus ln of x. By our previous result. So I'm using this statement here that we already proved. And, well, ln of x plus ln of x is 2 ln of x's. Okay, so it's true for 2. Well, if it's true for 2, it's true for 3. If it's true for 3, it's true for 4. And I'm going to use induction. Well, let me just do 3 first. R equal to 3 is ln of x squared times x. And by the rule we already proved, that's ln of x squared plus ln of x. But in just the previous step there, ln of x squared is 2 ln of x plus ln of x. Oh, stop that. And 2 plus 1 is 3. Oh. So that's 3 ln of x. So it works for 3. So if it works for 3, implies it works for 4. And if it works for 4, it works for 5. And forever. If it's using the same argument, I can prove that it works for, it's going to follow that it works for all the positive integers. Okay, and that, formally that's called an induction, a mathematical induction. Therefore, ln of x to the r is r times ln of x for r, a positive integer. So I'm still pretty far away from doing all the rationals. What about the negative integers? They're rational numbers too. Well, let's start with, in fact, this is actually going to hinge on one thing. I'm going to prove that this rule works for r equal to -1. Because x times 1 over x is 1. Anything in my domain. And okay, ln of x times 1 over x then is ln of 1 So I'm kind of coming in the back door here. Okay. I just note that this is true. And then ln of the left side is equal to ln of the right side. Well, the ln of 1 is 0. And ln of x times 1 over x, well, that's a product of two numbers. And we just showed we can break it up. The log of a product of two numbers is the sum of the logs of the numbers. And so what we've got then is that ln of x plus ln of 1 over x. Sometimes I put parentheses, and sometimes I don't. If I think there's any chance of misinterpreting what I mean, I put them, okay, to make it absolutely clear. Sometimes you have no choice about putting parentheses, but here you do. Okay, but that gets it for me because that says ln of 1 over x is minus ln of x. Just subtracting ln of x from both sides of this equation. So that says that ln of x to the minus 1 is minus 1 times ln of x. And that proves that for r equal to minus 1. Yeah. Okay, well, if I know that, all the other negative integers are easy. For minus n, a negative integer, and I'm going to prove it works for that. And I'm about out of time. All right, because the log of x to the minus n is equal to the log, well, x to the minus n is equal to x to the minus 1 to the n. That's an algebra rule. Okay, so I can write change the form of x to the minus n to be x to the minus 1 all raised to the n. And now n is a positive integer. So this is equal to, I can pull that n down because I've already shown this works for positive integers. That's equal to n ln of x to the minus 1. But I just proved up there that I can pull that minus 1 down too. So that's minus n ln of x. And that shows then that ln of x to the minus n is minus n ln of x. So that works. So I've got that shown. And then I need all the rational numbers, but I only have 2 minutes, so I'll stop here. And I won't make you suffer through much more of this. All right. I just think this is extraordinary that out of the calculus falls the algebra. It's lovely. And I want to show it to you. Okay, so hang around if you've got questions. Otherwise, we'll call it a day. And I'm going to finish up talking about the log function tomorrow. And we'll know all we need to know, I guess. And then we're going to talk about its inverse function. It's 1-to-1 because it's increasing over its entire domain. Therefore, it has an inverse, and it's a really important function too. So hang around if you've got questions. And let's see if my Zoom crashes again. Otherwise, you can go.